Hi friends, welcome back to yet another video. Here we will solve another problem which was asked in previous year gate. So as I usually say with every this kind of video, you should pause the video and try to solve the problem on your own. I think I'm showing the question in such a way that it is legible, so you can read the question on your own and you can try solving it on your own. Then come back and watch the rest of the video, because I will be telling you a few things which you may not be knowing, and I will be describing a few concepts as well. It is not just simply solving it. I will try to drive home concepts or theory as much as possible. So here you have basically three shafts, I would say, or one single shaft where diameters are changing from one point to the other. Here you have a diameter, here you have a different diameter, and here you have another totally different diameter. And let me make this a bit more clear. This is K1, this is K2, and this is K3. These are the torsional stiffness values. Now we are asked to compute the natural frequency of torsional oscillation. Before that, see, everyone knows the very well-known example of a cantilever. Like, let's say I have a cantilever of this kind. I apply initial excitation here and then leave the system, then it will oscillate. This is called bending oscillation, because we are giving that initial excitation and then leaving the system, and then the system is moving in a plane, in a manner like this, which is transverse to its longitudinal direction. So this, and now let's say I have a different case where something like this. Let's say this is a very flexible thing, a material like rubber. Then I'm just giving an initial excitation in this direction and then leaving the system. Then what will happen? The system will vibrate in this way. So this is called axial vibration. In lateral vibration, your lateral stiffness will decide what is the natural frequency. When you have a system vibrating along the axis like this, then the axial stiffness will determine what is the natural frequency of the system. So having seen lateral and axial, now we have another case as well. Let me remove all this stuff for the time being. We have something called torsional also. So let's say I have a system like this. This is a tube, let's say. This is a tube like thing, a very thin tube. Then I'm applying a torque, an initial excitation in the form of a torque. I'm applying a torque and then just leaving it. Then what way it will vibrate? It will try to rotate like this. Assume the material is very soft, or in other words, it is not having a very high value of G or Young's modulus of rigidity values are low. Let's assume for the time being. Then if I give an initial disturbance in the form of a torque, and if I leave the system, then it will vibrate torsionally. So I gave you three examples in order to appreciate that there are different kinds of vibration. A system can vibrate, the same system in fact can vibrate in different ways depending upon the kind of initial excitation that you provide to the system. Makes sense? So here we are talking about torsional vibration. So torsional vibration will be governed by the torsional stiffness of the system. So now naturally the question arises, what is torsional stiffness? What is this whole thing about? For that, I thought I will just describe that with a simple example of this kind. I won't get into the nitty-gritty of things. It will be very abstract explanation, but I will make sure that you'll get all the maths required to solve the above problem, and we will be able to bring some kind of intuition into torsional loading. So here, as you can see, I have a shaft. They call it usually shaft when you have a torsional loading acting on it. So I'm using this external member like this to give you a feeling that how torsional loading is actually done. I could have simply drawn something like this. Let's say I could have drawn something like you are applying a torque like this, which will be force times the distance between these two forces. I could have done that, but I wanted to give you a more realistic view of torsional uh, loading. A good example is when you have two gears, when you have two shafts meeting, transmitting power from one to the other using gears. Let's say L is the length of your rod. Now going to the deformed configuration, your once you apply the load, the rod will deform like this. Let's say this is the undeformed configuration. Whatever I'm highlighting for the time being, this is the undeformed configuration. This was the state before you applied the load, applied the torque. Once you applied the torque, then this particular fiber has rotated about this point like this. So this fellow has moved from here to here. Similarly, this fellow, which is on the face, has moved from here to here. So this is how the structure will deform once you subject it to a torsional loading. This is an important parameter. This is called angle of twist. Now, let's say I'm not going into the proof of all these things, but let's say G is the shear modulus of rigidity of this particular material, and J is the polar moment of inertia, and let's say L is the length of the rod. Then in terms of the torque applied, you need a relation which tells you what will be the angle of twist. So that expression is here. So this is the expression we are looking at. So you know what is the external torque that you are applying, and for this particular torque you will get this much of an angular twist. This expression is pretty much like F is equal to kx for a spring. So here you can say, instead of the linear deflection on the one hand, we have linear deflection of the spring, and in this case we have the angular twist of the rod. And in one case we have the axial force acting on the spring, and in this case we have the torque, external torque acting on the rod. So this particular quantity Gj by L is the torsional stiffness. Having established the intuitive meaning of torsional stiffness, now it's time to go ahead and solve the problem. Here you can see we have the system over here. It is connected to three torsional springs. By torsional springs I mean these rods. They are equivalent to torsional springs. Now the first question arises, in order to compute the natural frequency, we need to have a governing differential equation of the system, of this particular dynamic system. So the next question is, how is this particular system going to vibrate? What kind of motion the structure will undergo when it is set into vibration? So we have three options: linear, translation, rotation about a point, and general plane motion. So in this case, this structure is going to vibrate in pure rotation about a given axis. So the Newton's law, or I would rather, if you want to be very rigorous, then I have to call those equations Euler's equation. For the time being, they can be seen as the analogous equations to Newton's equations. See, Newton framed all these equations for particles, but when it takes to rigid, when we are extending those equations to rigid bodies, as in this particular case, then it is fair enough to call those equations are Euler equations, but they're not very difficult. Like, you have your polar moment of inertia of the system times the angular acceleration is equal to the sum of external moments or external torques. In this case, I will use the word external torques acting on the system. So since we have this lot of torsional springs in the system, we can reduce this equation in this manner. We can say j theta double dot is equal to, anyway the springs are going to resist the torsion, so I'm putting a minus sign over here, times the theta. See, this particular value of kt will be the total stiffness of this whole system. So we started off by saying that in order to compute the natural frequency, we should know how to write the expression that governs the dynamics of this particular system. So we have an equation here. Here J is known because J is provided in the problem. What is the net stiffness in the system? That is something we need to figure out. For that, we have few inputs in the question. They have given us the stiffness of each of these portions. The next question is how to arrive at the net stiffness of the whole system. The answer goes like this. First, you try to figure out in what manner they are arranged, whether they are arranged in series or whether they are arranged in parallel. So we have to figure it out like this. Let's say I apply a torque over here T, and then I'm now going to draw the free body diagram of the whole system like this. Then it clearly shows that this portion of the system will be subjected to the same amount of torque. This one will be subjected to the same amount of torque, and this one will be also subjected to the same amount of torque. And one other thing is that this portion and this portion, since they are connected to one single point, there will be, at this particular point, the angle of twist must be the same. Otherwise, you don't have continuity. So one constraint is that at this particular point, you have your deflections or your angle of twist same. And among these two springs, K1 and K2, among these two torsional springs, I have my external torque acting on the system as same, which in turn means that these two springs are in series connection. So I'm reducing the system from a 3-spring system to a 2-spring system as shown over here, where these two springs are approximated as an effective spring with a stiffness of this much. Now the next question arises, how these two springs are connected? They are connected in parallel. Why? Because the deformation or the angular twist at this particular point for these two springs are same. Or to elaborate it further, see, this point will have always a theta 1 is equal to 0, and this will have a value theta 2 will be something non-zero. And let's say here also theta 4 will be 0, theta 3 will be, from the continuity or what you can say from compatibility, it arises that this theta 3 value should be equal to theta 2 for the continuity in the structure, which effectively means that the net deflection or the net angular twist seen by these two portions are the same. Theta 2 minus 0 here also theta 2 minus 0, which means that these two springs are connected in parallel. We know the expression how to calculate the net stiffness. Doesn't matter whether it is torsional stiffness or lateral stiffness. When you have two things in parallel, you know what is a formula to compute the net stiffness, which is just the summation of individual stiffness values. So I'm doing it over here. Having computed the net stiffness in the system, everything is pretty straightforward. This particular system, I would say this is KT, because it is the torsional stiffness. Here in this case it is the stiffness against translation, but here in this case it is stiffness against torsion. So the natural frequency can be computed like this. Pretty straightforward. KT by J, where J is the polar moment of inertia and KT I have already evaluated. This is the final answer. One more final thing I would like to tell you. See, polar moment of inertia is defined like this, integral r square dm. So it is effectively a property which tells you how small individual masses are arranged about a particular axis. Here we are saying, since we are only, see, here in this case we are talking about a system which is rotating about a central axis like this. So we are referring to the polar moment of inertia of the system about this axis. This has to be very clearly understood. You have to evaluate this particular integral about the axis in which whole system is rotating. Thanks for watching.